So again, now you guys know how to make op amps. Single-ended output you can make, differential output you can make. You can stabilize using common mode feedback. So again, if ideally things were all good, course would end here. But fortunately for you guys, there is a lot more to learn, right? Because there are whole bunch of things that work against you to make sure the design doesn't work. So you have to battle against all of those odds and make your design work, right? And two major non-idealities that we'll be focusing in the rest of the course are this. One is noise, because it turns out just like in classrooms, even circuits, there is noise always. So you'll have to deal with noise. And second is uh, the fact that no two elements are identical on chip, right? So even if you think that two transistors are identical, in practice there is going to be a mismatch. So we'll briefly look at how to deal with these two non-idealities, starting from mismatch. And to understand the effect of mismatch, first let's understand how components are made on a CMOS process. So I'll just use slides for that because I just have to show you a bunch of information. Nothing to derive, just okay, why is it not happening? Resume slideshow. Okay, yeah. Okay. Oops. Yeah. So first of all, let's understand how transistors are made. Some of you would have taken some courses already. So what is the base on which CMOS process is made? A P substrate like this, and then you have NMOS transistor made like this. You have two N plus regions, and then you have a oxide and the gate here. That's a MOSFET. This is an NMOS. For a P MOSFET, it's similar, but P MOSFET is made on an N well. So basically, in the P substrate, you dig a well and then fill it with N whatever, and then you have P plus things here. That's all. Now, of course, these are transistors. Here, it turns out these vertical dimensions, whatever you have, right? They're not under your control. It is decided by the fabrication process. The only dimensions you have access to are in the other two sides. Okay. So typically, instead of showing this 3D view, we show the 2D view, and that 2D view will essentially show these two dimensions which are actually critical for you. And that's basically your engineering drawing. This is the side view. You draw the top view to look like this. So this is the width of the transistor, and this is the length of the transistor. Same thing for the PMOS also. So when finally we deal with transistors in layouts, this is the view we will be seeing, because only these two dimensions are controllable by you. Cool. So now these are transistors. Now you want to make connections in transistor. So how do you make connections? Sorry, I mean what do you use for connecting two things? Wires. So how is wire made of? Metal. So what element do you think might be used for making aluminum? Yeah, if you are very costly, we can use, but aluminum is costly. So typically, what can be used instead? I mean, what do you use for wiring in houses? Yeah, I mean same thing, right? I mean, if that is copper, why should not this be copper? So same thing. So you have multiple copper metals like this, and in fact you have multiple layers depending on the process. There can be 10 or 12 also. So these are copper, and typically most of the process now have an option to have one aluminum metal layer also, but all the other layers will be copper typically. And again, these vertical heights are not under your control. So here again showing that side view. So let's assume that this is metal 1, metal 2, metal 3. Now of course if I have it like this, I can't have these metals floating in thin air like this. So what should I put in between? Some insulating dielectric material has to be put, and that's what is done, so that it doesn't fall on top of each other. Now of course you want to make connections, say from, let us say, this fellow to this fellow. So you typically have what is called as a contact, and then from here you have to connect to this metal line, and that is done using what is called as a via. It's basically, think of it as a pillar connecting between two layers. That's all. You don't have to think so much. So this way this can be connected. Now if you say that I don't want to make this connection using the first level of metal, I want to do using second level of metal, you have to put one more via that connects the first level of metal to the second level of metal. So that way your connection is done like this. And yeah, similarly, if you want to go for third metal, you can do something like this, right? So it's connected like this. So, and as you already see, all the NMOS transistors here share the same P substrate, right? So as I already mentioned before, you have a fourth terminal in a transistor, the body terminal. And as you see, all the NMOS transistors share the same substrate. And you don't want this PN junction to forward bias. So you typically connect this to the lowest potential possible to avoid forward biasing, and that is usually ground. That is why I said that for NMOS transistor, this should be connected to ground. But of course, sometimes there are special processes where you can actually exercise control on what voltage you can connect the P substrate to, which means the P substrate cannot be common to all the NMOS transistors. So what is done is the following. For that, you have a separate P well, but that should be put in an N well so that it is isolated from this common P substrate. So you want to have this way, this can now be connected to any potential you want, because this is now only local to this transistor. Whereas this P substrate is common to all the other transistors that you will be making here. And this is called as deep N well process. It's costlier, and I mean, not all technologies might have this option. So now, of course, we have seen MOSFETs. So in addition to MOSFETs, what all we need for making circuits? All the passives, right? So we look at resistor first. So resistor is simple. You just take some material with some resistivity that gives you this one. So here, if I'm interested in the current flowing in this direction, right, and these are the dimensions. What is the resistance of this slab of material? Go back to your 6th standard physics. Rho into cross sectional areas W times T, right? So that's what is this resistance is rho into the length by the cross sectional area. And as I already mentioned, this thickness is not under your control. And if I look at the top view of this, it's going to look like a nice rectangle. And here in this expression, typically we take out rho and T outside because they are not under your control, they are already fixed. So this is denoted as sheet resistance. What is the units of this? I mean, from this, what can you say about the unit of this quantity? Ohms, right? But typically we say it's ohms per square for practical reasons, because if I know the sheet resistance, to find the total resistance, I just have to find the ratio L by W. That is, if I know the number of squares, for example, let us say this is some 6 micrometer and 2 micrometer. Basically, I have how many squares? 3 squares, right? That is basically this is square 1, square 2, square 3. That's a ratio between 6 and 2. Where did it go? Yeah, that's a ratio between the length and width 6 and 2. So if you know the number of squares, you know the sheet resistance, you can basically get the total resistance. So to differentiate this from the total resistance, we give this ohms per square. That's all. And the typical numbers can be in hundreds of ohms per square, depending on the material used for making the resistor. Now resistor is done. So what is next? Capacitor. So capacitor, how do you think we can make capacitor? Yeah, 2 metals and put some dielectric in between. That's what is done. So let us say we have so many metals available. So there are different options. Say I can make capacitance between the bottom 2 metals, or I can make capacitance between top 2 metals, right? But it turns out if you make the capacitor using the bottom metals, you get the required capacitance, yes, but you also have a parasitic capacitor from this to the substrate. So basically, although you want to make a capacitor like this, now you see that from the bottom plate you have an additional parasitic capacitor to the substrate, correct? That basically is not something good. So which means, do you think we'll prefer the option 1 or option 2. Why? Yeah, now I mean this parasitic capacitance from here to here is going to be much small. So that's why it is usually done in the top metals, and most of the time there are special metals reserved for making capacitors. One might be just below the top metal, one might be just above the top, but the next metal, and capacitor is usually formed between these two. Typically, not the usual metals are used. Sometimes special metals are used, kept in reserve for making capacitors. So which means this is how a capacitor will look like. Looks like a nice fruit cake, but yeah, you can't eat it here. So here again, you have dimensions as these. What is the capacitance value? Epsilon times. What is the area? Cross sectional area. WL. So that's what happens. Epsilon times WL by D. As I already mentioned, the vertical dimensions you don't have control. So as usual, you take out things that are not under your control and give it a name. We call this the unit capacitance. What is the units of this unit capacitor? Is it farad? I mean SI units, farad per meter square. But a practical unit is basically we say femtofarad per micrometer square, because those are the ranges of values we will deal with. And typical numbers can be few femtofarads, 1 or 2 femtofarads per micrometer square. Yeah.
We have metal and dielectric inside between.
Correct.
So
Correct.
it's also creating a capacitance of its own now.
Which
How
capacitance?
it is different from the capacitance we are creating.
No, this is the this is the same dielectric use.
Means one more figure we take.
Mm-hmm.
We have taken multiple metals now.
Correct. Yeah.
So how is that metal plating? And
Oh, that is a parasitic capacitor. Okay. Yeah, you are correct. Basically, here what is done is special. I mean, as I mentioned, different metals and different dielectric will be used. Okay. Now, what you are saying is, what is pointing out is correct. Let us say you are having things like this. There is also capacitance formed here. Those are not unwanted capacitors. Those are what we call as parasitic capacitors. Just like parasites, they come and latch onto your design and affect you. You are absolutely correct. Yeah. But for making these, you will have specialized things, because these will be really large. If you want, let us say 100 femtofarad of capacitance, the whatever area of this metal is going to be really large. But yeah, I mean these will also introduce additional capacitance, but they are unwanted. So you have to deal with them. Cool. And of course, now if you make all these things and make your design, you fabricate it. You don't fabricate just one design. You fabricate one whole silicon wafer. So oops, what is happening here? Okay. So this is how silicon wafer will look like. Like nice shining plate. And typical dimension is, I think one of the standard dimensions is about 300 mm diameter. And once in this, you basically replicate your designs multiple times, and then finally the wafer is sliced like this, and then you can get out individual chips from here. So that also I'm showing, for example. So this is called dicing, and whatever you get separately, they are called as dice or chips or whatever you can call. Now, depending on the wafer size and the area of your each individual design, you can get several hundreds and thousands or millions of chips per wafer. I think I even have some. Yeah, this is one real silicon wafer. In fact, I found it from this website. And interestingly, this website is a place where people sell antiques and collectibles and all these rare items. And some guy was actually selling this thing. This is a real 1980s National Semiconductor CPU. Of course, this wafer size might be smaller, and it's because it's very old. Yeah. And if you zoom in, you can even see the designs actually. So now, let us say you have this. Let us say I consider one chip in the wafer. In this one particular chip, let us say I had a resistor. Let us say has a nominal value of 1 kilo ohms. Let us say I also have another resistor, identical dimensions kept close to it. What is the expected value of this resistance value? Ideally, what do you think the resistance value should be? 1 kilo ohm. But of course, as I already mentioned, no two things are identical, so there is going to be a mismatch. And simply because here I have nicely drawn rectangular shapes, but in practice it is not possible to etch out rectangles, so we'll have some rugged geometry like this. And of course, these two geometries here might not be identical, so the resistance you finally have will be different. And let us say you have 1000 resistors in a particular chip. I don't know why, but let's say you have 1000 resistors, and then finally after the chip is fabricated, you measure the value of all 1000 resistors. They are going to be different. But if I sketch the distribution of that, x-axis I show the resistance value, y-axis I plot the uh, number of resistors having that value. How do you think the distribution will look like? Gaussian, because again central limit theorem, in a lot of IID random processes will add up to a Gaussian distribution. So something like this. Okay. And what do you think should be the mean value in this case? In the chosen example, what should be the mean value? Yeah, 1 kilo. Because remember, mean is the expected value. You expect that the value should be 1 kilo ohm, so the mean should be 1 kilo ohms. And around this mean, you have a spread, right? And that's a variation in the resistance value, and this is what we call as random mismatch. Right? That is the variation of resistors values within a single chip or a single die is called as random mismatch. And now here let's say I considered this chip now and found the distribution of resistors, and I found that the mean value of the resistors is, let us say, 1 kilo ohm, and then I have variations around that mean. Now let us say I take a chip from this particular section. Now if I find the mean of these resistors, it turns out this need not be same. This can be something, let us say it's 1.2 kilo ohm plus or minus something, whereas here one more chip I take, this can be, for example, 0.8 kilo ohms plus or minus variation. The mean itself can vary across chips, and that's again simply because the fabrication process happening in this particular location will not be exactly same as what's happening here and what's happening here, because the fabrication process itself can slightly change based on the physical location. So even the mean will change from chip to chip, and this which means that, let us say, if I take one particular chip from that wafer that has a mean of 1 kilo ohms, for example, one more chip can have a mean of 1.2 kilo ohms. Another chip, sorry, this should be 0.8, right? This is 0.8. So let us say if I take one more section that has 1.2 kilo ohms, and similarly if I take each random chip from that wafer and check the distribution, one might have a distribution like this, one might have like this, and so on. But the fabrication process or the foundry will sort of guarantee that if you take any chip within that wafer, the mean value might lie somewhere here. So that is, the mean value can be between, for example, 0.8 kilo ohms to 1.2 kilo ohms. That much they will be able to guarantee. So this variation in this mean value is what we call as process variation. So process variation, in a way, it's the variation from chip to chip within a single wafer. Now in a single chip, you have variation in the resistance values also. That is what we call as random mismatch. That's just the terminology that we use. So variation in the mean is called process, and around that mean, whatever spread you have, that is termed as due to random mismatch. Now just like you have this variation for the resistor values, even capacitors will have the same thing. Now same is the case for MOSFET also. MOSFET is no exception. But for a MOSFET, the parameters of interest are the threshold voltage and this UCOXW by L. Right, and that's typically we denote as beta. And for MOSFET, these process variation has particular name. So let us say you have a MOSFET. Let us say due to the variation in the mean value, that is process variation, you end up in a case where threshold voltage and all these factors come to such a value that the current is very, very small. If the current in the transistor is small, what can you say about the speed of the transistor? It's going to be slow. So that is typically called the that is typically called the slope. Whereas if it is coming in the actual value, we call it as typical. Similarly, if all these values come up to a value such that the current is really large, the speed will be fast, so we call it as fast. So this is for basically NMOS. Similarly, you have one more for PMOS. So we have the combinations of them, and these are the common combinations. So this is basically slow NMOS, slow PMOS. This is typical for NMOS, typical for PMOS, and here this is slow NMOS and fast PMOS, fast NMOS and slow PMOS. So the last two are called skewed corners because here one of them is fast, other is slow. So these are called as process corners. It is a variation in the transistor properties. We call it as process corners. That's all. And these are the 5 process corners we typically have. And so in addition to the variations in this process and mismatch, process variations and random mismatch, you also have variations in supply voltage because you assume that you are powering with 1 volts, but maybe your battery is discharging, so supply voltage will change slightly. And not just that, you have temperature also varying. You can't say that your circuit will work only in January when the temperature is very low in Kanpur. When it comes to March, it might work, and in July, peak summer, it doesn't work. That's not a practical thing. So even temperature will change. And these are the 3 trinities. This is the trinity that work against you and sort of make challenge you to design better, right? So this is called as PVT variations. P is for process, V is voltage, T is temperature. So finally, when you make a real design, your design should work across all of these variations. Variations in process corners, variations in supply voltage, as well as a range of temperature it should work. So now, just to summarize, remember, if I take resistors, so in a single chip, the resistor will have a particular mean and will have a spread around that mean, and this mean itself can vary from chip to chip. Okay. So this mean itself can vary from a nominal value, let us say plus or minus 10 to 20% of that. This variation is called as process variation. Variation in the mean value from chip to chip, that is process variation. Now around this mean, in a single chip, we have variation in the resistance value. That is what we call as random mismatch. That is within one particular chip, what is the spread of the values of a component, that is the random mismatch. So which means now let's start to see how to deal with mismatch. So to deal with mismatch, first let's understand how to quantify mismatch. So this is a random phenomenon. So obviously use statistics. So in a single, let us say you take the same case of resistor. Any resistance will be mean value plus delta R, and this is the distribution for this resistance, this quantity R mu plus delta R, right? It has a mean around mu and a variation. Now my mismatch quantity is just delta R. So if I'm interested to find the distribution of only delta R, so how will that look like? If this is the distribution of R mu plus delta R, I'm interested to find the distribution of just delta R. How will it look like? Similar, but what is the difference? Mean will be centered to 0. Correct? So here, of course, mean is 0. This is a Gaussian distribution. What is the only parameter I have to specify? Standard deviation, right? So I'm interested to find this. Again, it's a random signal. I know distribution is Gaussian, so I just need mu and sigma. Mu is 0, so this is the deal. And this is what we specify, standard deviation in the mismatch. And let us say, for example, for a mean value of 1 kilo ohm, let us say the standard deviation is 100 ohms. Now let us say I have a case where my nominal value of the resistor itself is 10 kilo ohm. Then what do you think the value of sigma delta R will be? For a mean value of 1 kilo ohm, my standard deviation was 100. The same distribution, if let us say the mean has become 10, what do you think might happen to the standard deviation? Take a guess. 10 times? Same or it will be different or huh? It will be how much? Yeah, I mean, expect that mean itself is going 10x, even the variation also be 10x, right? So which means it's going to be 1 kilo ohm. But looks like now the process is having a lot of variation. Earlier in this case, this was having less variation. So which means just looking at this alone is not the best way to quantify how much is the variation in the component values, right? So what do you think we should do then? Because the variation actually depends on the actual component value also, right? It's like a round off error. I mean, yeah. So which means instead of just looking at this, what should I do? Relative value of, yeah, basically I should take sigma delta r by the mean value. That way I kind of normalize it. So this will give a better metric to compare. And that's what is done. Uh, so we look at the relative mismatch, which is sigma of delta r by r. That is the standard deviation of delta r by the nominal value. And this is basically same as sigma of delta r by r. It's a constant, right? Expected value of x by k is same as expected value of that k is a constant, so I can push it here. So this is what we typically specify, sigma of delta r by r, and that's what is called as relative mismatch. Now just like for resistor we have sigma of delta r by r, for capacitors what do you think we'll have? Delta c by c, same thing, that's what we have. So sigma delta r by r and delta c by c, and it turns out this standard deviation can be actually very small, that is 0.1%. And remember, this is the random mismatch because we had a fixed mean. Around that we are seeing what is the spread. That spread I'm saying can be kept very small. Okay, but the variation in the mean itself from chip to chip, that is the process variation, can be 10 to 20%. Which means if I have 1000 resistors I fabricating and I have a whole wafer, in each single chip the variation of the resistors might be very small, that is about 0.1%. I can keep it like that. Whereas the mean value from one particular chip in the wafer to another chip in the wafer, that variation can be really large, as high as 10 to 20%. Is it clear the difference between process and random variations? So now just like how we did for capacitors, resistors, same thing we'll do for MOSFET. For MOSFET, the current factor beta, we say delta beta by beta, that is sigma of delta beta by beta. For threshold voltage, we don't normalize it, we just say it's delta VTH, simply because it turns out in practice some transistors can even have threshold voltage close to 0. So if you basically divide it by this, it becomes a unreasonably large number. So threshold voltage we don't normalize. So just to one last point. So all of these relative mismatch quantities, it turns out they are inversely proportional to the square root of area. So that is one takeaway should have. So which means I can write each of them like this: sigma delta r by r is some proportionality constant times 1 by square root of the area. Similarly, the relative mismatch for the capacitor is another proportionality constant times 1 by square root of area. Same for MOSFETs also. So what is the units of this sigma delta r by r? Unitless. So what should be the units of this? What is the unit of AR? Meter. What is the unit of capacitance? Meter. What about A beta? What about A VTH? What is the unit of this? What is the unit of sigma delta VTH? Huh? Voltage. So what should be the units of this? It's volt times meter. I mean, because this VTH mismatch we don't normalize with respect to the actual value of VTH, because as I mentioned, the VTH value can be really small. So this is the main thing. It turns out the standard deviation of all the relative mismatch quantities, all the mismatch quantities, I'll say sigma delta, is proportional to 1 by root of W by L. And it turns out the first person who recognizes, or one of the persons who recognizes, was Marcel Pelgrom. So what we have here, this is called as Pelgrom's model or Pelgrom's law. So that's the final takeaway I want you to have. All these relative mismatch quantities, they are inversely proportional to square root of area. So we'll continue from this point in the next class.